All right. Hi, everyone. My name is Rahul, and this is a talk sponsored by Glizzycoin. No, I'm kidding. This talk, we will talk a lot about blockchain, but not like the business aspects of blockchain. That's a bit boring. What we'll do is we'll go through the technical definition of blockchain, and we'll try to break it down and figure out how do you build a secure data structure or secure network like a blockchain. And then after that, we'll build up on this knowledge and then figure out ways to attack it, right? So this talk will not cover anything about like the use cases of blockchains, how the industries talk about blockchain, even though that's what. So I am actually a blockchain engineer, and I work a lot with that. But the main reason I got fascinated by blockchain was the technical aspect of it because it has a lot of really interesting computer science concepts, and that's what we'll go through today. But from a more cybersecurity perspective, I will give a disclaimer in that I am not a cybersecurity specialist. It's just a thing I read about just for fun. So let's start going into the details. So firstly, let's forget about the word blockchain and talk about this other term called distributed ledger technology. The idea is pretty simple, right? You have how can a group of computers or a group of nodes talk to each other without necessarily trusting each other, but still coming to an agreement on what they're talking about. So, for example, a consortium of banks all agreeing to certain sets of transactions happening in place. Now, all the banks compete with each other, so why would they trust each other? In the real world, of course, there are things like laws and governments that force you to trust each other. But that's a bit inefficient. What if we can do this without any middlemen, without any extra players? Um, and that's what DLT is. But to make that happen, we need to have certain properties. One of them is the fact is that it's immutable, i.e., once you put something into this ledger or database, you can never change it. And that's needed because these nodes do not trust each other. So they need to be sure that if something is in the ledger, you can never change it. Another property of that is secure, obviously. A third one is time stamped, which means every time a transaction takes place on this database or any changes happen in the database, you also record the exact time of it. Because you need to remember here again, people need to come in agreement about what transactions happen and also their order, and they don't trust each other. And there is no sort of central authority that's governing all of them. And so you take this philosophical concept and try to implement this with a lot of game theory knowledge, with a lot of cybersecurity knowledge, right? And remember, I said distributed ledger technology. In the industry, people throw the word decentralized a lot, but in reality, the idea is every node in this network will have their own sort of copy of the ledger. And that's how they can all be sure that they all have the same information as the other party without having to trust the other party. And Bitcoin is obviously a blockchain, but how does blockchain link to a distributed ledger? Well, it turns out that there are many ways you can make such a DLT or distributed ledger technology. Blockchain is just one of them. What differs blockchain from other DLTs is the way that it stores data. Effectively, all the data is stored in blocks, so blocks of transactions, and all these blocks are chained together, and hence the term blockchain. And there are many other cool ways to sort of store this data. So if I go 2 slides back, you have Hedera hash graph that stores it in a format of a graph with hashes, and that's what's called hash graph. IOTA use another technology called Tangle, where they literally tangle up all the transactions together. And blockchain, obviously, chain of blocks, right? So we've finished with like the basic technical definition of a blockchain, but before we go into how do you securely implement this structure, we just need one sort of knowledge, which I'm sure all of you know because this is cybersecurity, but just in case you don't, the concept of one-way hashing. The word one-way means that if you can multiply and figure out what the product is, but given an output, you can never figure out what the input is. So I could tell you that if I give you 10 and 2 and say the function is multiply, you'll all get 20. It's easy to compute. But imagine such a function where if I tell you 20 and I tell you 10, you cannot figure out what that x is where 10 times x is 20. And there are many fancy ways to do it. One of these fancy ways is called elliptic curve cryptography, which is the principle behind the S in HTTPS effectively. And it's used by like 95% of the top world's website. If you take this a step further, you have the concept of hashing. Now, hashing is you give any kind of text, image, blurb, and you'll always get a fixed output. When I say fixed, I mean it has a definite length, and it has the property of one-way hashing, and it's deterministic in that given if I always repeat the same input, I'll always get the same output. So for my name is Rahul, I'll always get, no matter when you do it, you'll always get this particular string. Now notice I've changed the text to I am talking, and that's completely different, but still it has the same length as my name is Rahul. And then I have a typo in the next line, and you'll notice even though I've changed just one letter, everything is completely different. And that's the property of hashing. You don't have collision. Two hashes will never be, two sentences or two inputs will always have two different hashes. They should not have the same hash. That's the mathematical idea behind hashing, right? So now let's go on the details about this data structure that we talked about, the blocks, effectively. So you have within a block, what does a block contain? It has the timestamp of when the block happens. It has a transaction root. We'll go into that in the next step. It has a previous hash. So remember, I said the blockchain is a chain of blocks. How does one block link to the previous block? Well, it has the hash of the previous block, and that's how it connects. Like block 0 or the Genesis block, it just doesn't have this previous hash. It just has the timestamp, transaction root, and nonce. Nonce is again something we'll cover later, but effectively you can think about it as a one-time password kind of thing, a random number that makes sure things are happening in a specific way. The next part is, so remember I said there's transaction root. So let's talk about what this transaction root stands for. The transaction root is effectively, imagine a tree, and the head of the tree is the root, right? And so the way this tree works is you have like a block has several transactions in this. In this case, let's say you have a block with 4 transactions. What you do is on the leaf nodes, so on the bottom layer, you hash all of these transactions, and that's how you get HA, HB, HC, HD. Then you go a level further, and this is a binary Merkle tree, right? So what you do is you take the children and hash them together. So you get a hash, so you hash HA and HB to get HAB. You do the same with C and D, right? And then you go on recursively doing that. So at the end, you basically hash all these transactions in pairs of 2 to get a root. And that will be the root of all of your transactions hashed together. Now, you may ask why, and that's called Merkle trees. Now, you may ask, why do we do such a weird thing? Why can't you just have, say, a simple list where you have all of the 4 or 8 or 16 transactions in them? And that's a valid point, except that's not scalable. Why? We move on to the concept of Merkle proofs. So the idea is, so remember, I said in a blockchain or distributed ledger technology, computers can't trust each other, but they always need to verify if the transactions on a blockchain is indeed what they think it is. Now, everything on a blockchain is hashed, right? So how will I actually check if my transaction is there? Well, I'll simply hash my own actual transaction, but now I need to check if it's there on the block, right? Now, imagine you had a list of just, in this case, like, in this case, I think there are 16 transactions. Imagine you have a list of 16 transactions, and I want to check if my transaction, K, is in there. Well, you'll have to give me 15 other transaction hashes, and I'll have to combine all of their hash to get a transaction root, and only then can I figure out if a transaction works. In a typical blockchain, a block has thousands of transactions. So if anyone wants to ever do authenticity checking or authentication, authenticity checking, you'll have to give them like 1,000 transactions just for them to check if their one transaction was actually there. That does not scale well. Let's look at what happens in a Merkle tree. So I want to check if HK is actually in my block, right? As opposed to getting 15 other transactions in the previous case, here I just need 3 transactions. I just need HL so that I can create HKL because I'm combining the hashes of my roots. I need its neighbor, its sibling, that is HIJ, right? And then I can combine them to get the next level. And I take its sibling. So far we needed three things: HL, HIG, and HMNOP. And I'm already here. And then I need this to get the transaction root. So you go from, in computer science, we would say you go from an ON complexity to O log N complexity. You go from linear time to logarithmic time. And that's the secret of what makes blockchain scale so much. Even though you might think blockchains are very slow and Bitcoin has like 10 blocks every minute, but actually, if you wouldn't have Merkle trees, it would probably be hours and hours of hours and hours for just one transaction or one block to take place. So Merkle trees really help you scale up a blockchain, and it's a secret sauce behind every DLT sort of data structure. So assuming we've understood that, we move on to the next part. So we have understood how these blocks work and what makes these blocks tick. But how do you chain the blocks? As I said, every block has a hash of the previous block. So in this case, 1 is obviously a genesis block. It has no previous hash. But 2 will have the hash of 1, 3 will have the hash of 2, and so on. But the next question is, well, you have these blocks, great, but how do let's say a block is created, how do all the nodes ever figure out that there's a block? And then how do all of these nodes get the blocks and then verify that this block is actually valid? Because again, you can't trust people on the blockchain. And let's say you verified it, and then you have to add it onto the blockchain and make sure everyone else also adds into their blockchain. So you need to make sure everyone is on the same page, right? So there are lots of questions here. How do you sort of do this scalably, but also more importantly, knowing that there are malicious actors involved that you cannot trust, right? Moving on, there's another question here. You have this simple blockchain, right? But how do you prevent tampering of the blockchain? So if you go back and think about a bit about Merkle trees, if I would change a single transaction on my Merkle tree, it would completely change the transaction hash, right? The root of the transaction. And that's because obviously you have to always hash, and one hash will recursively be added to its sibling and so on and so forth. So say if I really want to change something in block 2, I change a transaction, it'll give a new hash, right? And in this case, I can very easily get away with tampering because all I need to do is change the hash in block 3 and we're done. We have successfully tampered with the blockchain. But if you notice, this hasn't happened in the 12 years of history of Bitcoin or in like the 7 years of history of Ethereum. Both of these are like the largest and the most popular DLTs in the world today. And how did they do that? How did they not just do consensus and the verification of blocks and make sure everyone hears about the blocks, but also how did they help in what system did they make to prevent the tampering of the blocks and make sure that the data in the blockchain is always authentic? So there's a lot of questions here to unpack. And this is where we get into the meat of our talk on how do you create a data structure in a network inexistent with malicious actors and make sure that everything still works the same. And to me, at least, this is fascinating that everyone knows that, you have a cryptocurrency like Bitcoin that has a price of say $50,000. And so far, no one has actually been able to tamper with the blockchain. Like never in history has there ever been a currency where people could not forge. And yet here is one in 12 years of history is the most sort of valued currency because no other currency to the dollar has a valuation of 50,000 per coin. And still no one has been able to sort of tamper with it. And now we'll answer each of these questions one by one, right? And the way we answer these questions, I have to introduce a few interesting concepts, a few interesting thought experiments. The first one is a very cool experiment called Byzantine Generals Problem. You're back in the Middle Ages, internet's not a thing, group chats are not a thing, Discord's not a thing, Glizzycoin also sadly is not a thing. And you have these three Roman generals, or these three Byzantine generals, and they all have a piece of land in between them that they need to conquer. And the problem is, the only way they can actually conquer the land is if all three of these generals attack with their armies at the same time, right? And how do you do that in, like, the prehistoric era? Well, you write a message, attach it to a pigeon, and the pigeon flies to the other general, right? Again, malicious actors, you are getting the pigeon to fly across the enemy territory. Well, someone might capture the pigeon, someone might change the letter, or you might be lucky and the pigeon would actually reach the other person. But you know that you will not attack this army until you're sure that the other generals will also attack. Because why would you? If you were the only one attacking, you're guaranteed to lose. You can only win if all of the generals attack at the same time. And so, in a way, you're quite coward that way, right? So you send a message to, so General 1 sends a message to General 2 saying, hey, let's attack at 1 p.m. Now, let's assume we're in an ideal world and none of the messages ever get captured or altered, right? So General 2 now gets this message, but that doesn't mean General 1 will attack, because it needs to have a confirmation that General 2 actually read the message, right? So it'll wait for an acknowledgement. And then, so now let's say General 2 sends an acknowledgement. So now General 1 knows that General 2 got the message. But now General 2 does not